All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another lecture of Math 391 Differential Equations. Had a lot of hefty theoretical stuff to go through last time. Got through a lot of it though. And hopefully in hindsight, it does explain a lot. How do you know an nth order linear differential equation has n linearly independent solutions, etc., etc., etc.? All the things that we've been taking for granted. Hopefully last lecture kind of cleared it up, why we're allowed to take it for granted. It turns out that linear ODEs can be reconstructed as a system of first order ODEs. And just by the sizes of matrices and all the theorems of linear algebra like Kramer's rule, etc., conspire to give us that, well, you're going to have a solution with n components in it. And so you'll have to have n solutions. Also, Kramer's rule guarantees unique solutions in some situations, which we will tend to be in. And so it turns out whenever we have, it can be first order, it can even be higher, but whenever we have an nth order linear ODE and we're given any set of initial conditions and the coefficients are continuous on some open interval that we're considering and the initial conditions are at a point in that open interval, then we are guaranteed to be able to find a solution. We're also guaranteed that that solution will be n times differentiable. We're also guaranteed that we can choose values of the arbitrary constants that will get that solution to match up with any arbitrary set of initial conditions we are given. We have a lot of guarantees. We are also guaranteed that this solution is going to be unique, meaning there's going to be no other function that will solve it. If someone finds another function that they think will solve it, either they're wrong or there's a way to simplify their answer to get my answer. That's a lot of stuff. And that actually is why we were allowed this whole semester, quote unquote, the last month, we were allowed to do things like, oh, let's pretend a solution looks like this and try to find it. Oh, it works out. I guess that's the solution. That's everybody. Why were we allowed to do all those things? Why were we allowed to, when we had a second order linear differential equation, to assume that solution is going to look like C1y1 plus C2y2? Plus potentially some particular solution. Why could we assume that? How did we know when we found one solution from a repeated root that we couldn't just stop? Why did we care about finding a second solution? Why did we know we had to multiply that by t to get a second solution? This is all coming from the existence and uniqueness theorem for linear ODEs. And we went through that, was a lot of hefty theory, but hopefully it just kind of helped to make sense of it all, make sense of everything that we've been doing so far. And we actually did the linear algebra way of solving a very simple ODE that we could solve very easily. But I wanted to show you that the math actually does check out, right? So while this is harder, while the last example we did is much harder than something we would do in practice, theoretically, it was very important to know that this stuff could work out, because this is the reason that we know that we could solve things in the short way, right? So that was pretty important. What I want to do now at the beginning of this class for the first few minutes, I don't know how long it's going to take, but I don't anticipate it taking too long, or hopefully not, is we're going to again look at the existence and uniqueness theorem for first order nonlinear. So yesterday we covered the existence and uniqueness theorems for first order linear. We use that to show that a first order linear system can be solved, and then using the fact that we can take an nth order ODE and rewrite it as a first order linear system, we could then use that to prove that we can solve an nth order ODE uniquely. Now we're going to talk about the nonlinear case. And the nonlinear case for the nth order is actually very complicated. It turns out that there are situations in which we're not guaranteed a unique solution. We're not guaranteed any solution at all, in fact. And so we're not even going to talk about that. That's way above our pay grade. But something that we do take advantage of in this class is for nonlinear first order ODEs. We've covered a lot of examples. We've covered ODEs that were separable, that were homogeneous, that were exact, and these guys were nonlinear in many cases. And so we also found a solution using a lot of assumption type kind of business as well. Hey, let's pretend this substitution is going to work. And how did we know that that substitution would have found us all the answers? It turns out that there is an existence in Uniqueness theorem for first order nonlinear ODEs as well. And basically that theorem says, given some ODE of this form, y prime equals f of t comma y, and that f of t comma y can look very scary. Given that, and an initial condition, provided that the function on this side is continuous and its partial derivative with respect to y is continuous on some rectangle, then on that rectangle, we can find a unique solution that will fit, that will solve the ODE and will fit the initial conditions. And that was really surprising, I guess, in the first place, and all that good stuff. However, I do mention something here. As instead of the condition that the partial with respect to y is continuous, you could take just the fact that the function is Lipschitz continuous, and that just means this definition right here. But you don't have to worry about that. Chances are, not guaranteed, but chances are if you're not a math major, at this point, you would have never even heard about something called Lipschitz continuous, and you probably never will hear about something called Lipschitz continuous. So we don't have to worry about it too much. But that's another condition that we could have. So provided our f behaves nicely, what do we mean behave nicely in this particular way? It is continuous and its partial derivative with respect to y is continuous, then our first order nonlinear ODE will have a unique solution that will fit any random initial condition that someone gives us. The way this is proved, it's actually a lot less intuitive than the linear algebra way, so we're not going to spend too much time on the proof. I'm pretty much going to give you a proof outline for how it works. The feel here is going to be kind of like a Newton-Raphson method. Remember back, I don't know when you would have done this, but back in around the level of Calc 1-ish, we don't do it in Calc 1 at City College, but I have done it in Calc 1 in high school and at other places. So it's when you guess like what the root of an equation is, and then you use calculus to help you update that guess to get more and more and more accurate. So we are going to do something similar here. That's how this is proved. It's proven using something called the Picard iteration method, which is named after the mathematician, a French mathematician by the name of Picard. Essentially, you assume that there is some solution that solves the ODE, and the goal is to find it, right? You have hope that there is an answer out there. How do we go about finding it? Well, you start with an initial guess, and the initial guess is usually the zero function will solve it. And then you would take that answer and you would plug it into the function and you would integrate. And then you would create another function that hopefully is closer to what the solution should be. And then you take that answer and you plug it into the function again and you integrate again. You get another function. And then you do this again, and then you do this again. This should actually be 3. And that should be 2. And sometimes you're typing up all these things, you just leave stuff off. Let me just correct that here, because that's chances are that's wrong here, and it is. This should be 3, and that should be 2. All right, back to the matter at hand. Anyway, you can keep doing this iterative process, and you just keep going. And every new function that you create, it's just you taking the previous function, plugging into the f, and integrating that. This is called the Picard iteration method. And what you do here is that the phi1, phi2, phi3 going all the way up creates a sequence. We'll actually talk about sequence a little bit later. So it creates a list of functions. And the hope is that this list of functions will eventually converge, and they will converge to actually the answer for the ODE. And it turns out that if your function is continuous and its partial derivative with respect to y is continuous, then this actually works out. This sequence of functions will converge to an answer, and that answer will be unique, and it will solve the ODE. And on the way, you can check this as well. All these functions will actually fit the initial conditions given, but they might not solve the ODE. Eventually, we want to end at a point, or end, quote unquote, it might go on forever. It might eventually want to converge to a function that not only satisfies the initial conditions, but also solves the function. This is called the Picard iteration method, named after Charles-Émile Picard. People usually call him Emile Picard. He doesn't really use his first name, Charles, for whatever reason. But Charles was the name of his father, and that's his actual legal first name. All right. Now, the text goes into a very dense discussion, and I put the reference here if you want to actually read it, but you don't actually need to know it, about how do we know that each function in this sequence will actually make sense? How do we know it's going to even converge at all, much less converge to something meaningful? And how do we know that the thing it converges to that's meaningful is actually the solution to the ODE? And how do we know that it's unique? How do we know that some other function wouldn't have solved the ODE? Your textbook goes through all those discussions. I'm not going to go through that, but this is essentially the main outline of how we got it to work. And why would someone guess that would work? I don't know. I think maybe it might come from the fact of if you saw separable first order ODE, you can just get to the answer by integrating both sides. So someone just thought, what if I could always just integrate both sides? How can I actually get that to work? Well, it might not be separable, so integrating both sides with respect to t might not be possible. So what you do is instead, you replace the y with some function of t, and then you try to integrate that. And so because just what function of t you should replace it to is not obvious, you start out with a guess, and then you run it through this iteration process to come up with a better guess, and a better guess, and a better guess, and hopefully, eventually, it converges to the perfect guess. So I don't know for sure that that was what went on in the mind of the very first person to come up with this method. Differential equations is a lot like that. Because we know how the theory actually works out, people can come up with solutions in all sorts of random ways. They just kind of see a pattern that they take advantage of, like the integrating factor method for first order linear, right? Who would have thought of doing something like that? Someone just noticed, hey, some of these guys on the left side look like the product rule. I wonder if I could always get that to work. And it turns out that you can. And so that becomes a method. So a lot of the methods in differential equations, it's kind of iffy what the actual historical beginnings were, but we know that they make sense in hindsight, and we have the existence and uniqueness theorem to justify in hindsight that what we did was fine. And so I think it's actually more instructive to look at a couple examples and actually just see what happens with these two examples. So I have some examples here that will illustrate the first order nonlinear existence and uniqueness theorem. And then I have some more examples down here where we just go through and exploring not just the first order linear or nonlinear, but to talk about where you can find a solution, how do you know a solution would exist, what the nature of that solution is. So we have some of those that I just want us to get through, because these are also some problems that could show up on a multiple choice test, multiple choice final, multiple choice quiz. Really some nice, quick questions that could be asked, where they're not very difficult to deal with computationally, but it shows whether or not you understand some important concepts. But before that, let's just illustrate with these two examples, the existence and uniqueness theorem for first order nonlinear. Here is an example of a first order nonlinear ODE. And so here's the question. I want you to solve the initial value problem or show that there is no solution. Before solving, determine if we're guaranteed to be able to find a unique solution. If not, what does that mean? So looking at this, are we guaranteed to be able to find a unique solution? So based on what we have here, and you can actually take a picture of this, 5, 4, 3, 2, 1. Okay, based on that, we're looking at this guy. Are we guaranteed to find a unique solution? No. Eugene, why do you say no? Do you just randomly guess no? Well, it's a 50-50 shot. So I'm gonna guess no. Well, you have to be more specific. Our f here is a multivariable function, so you can't really say y prime. So here, our f of xy is x times the cube root of y minus 3. What derivative would we check? Well, this is continuous. Around 3, 3. Sure, I can plug in y equals 3 and I can plug in x equals 3, and there's nothing wrong with this function on an open interval or an open rectangle in the 2D plane that will actually contain that point. So no problem. Next thing we need to check is the partial with respect to y. Now the partial with respect to y is going to be, well, 1/3 x times y minus 3 to the minus 2/3, and this guy is not continuous. At 3, 3. So this means we are not guaranteed to be able to find a solution. Now, I want to make sure that you guys actually know what this means. So saying that I'm not guaranteed to find a unique solution, what does that mean the options are? What are the possibilities now? So if for some reason, this differential equation was very, very important to me, and I wanted to know if it has an answer or doesn't have an answer or whatever, me doing this check right here, what does that tell me about the possibility of a solution? Based on the theorem. And look at the picture you took of the theorem, read it carefully, make sure you fully understand what it's saying, and just understand that you have to read very carefully in mathematical statements because they are usually logical statements. And so don't use your intuition that you would get from everyday language, how people would speak, to determine what's true or what's false. It has to work logically based on truth tables and all that good stuff. So any guesses as to what this means for this problem? You guys don't even know what I'm asking. Okay, let me be a little bit more specific, Your Honor, if I may lead the witness. Does this mean that I cannot find a solution? The solution does not exist. Is that what this means? Right, there might be a solution on a different interval, but what about this? This doesn't care about that. Here I have this ODE for this initial condition. So assuming that I'm on some interval that contains that point, or in some region that contains that point, what can I say here? One, this means there may be no solution, but that's not all it means. It might also means there may be a unique solution. The thing is, we're just not guaranteed. We don't know if there's going to be a unique solution. The theorem guarantees the existence of a unique solution. It might still exist, but we're not guaranteed. So we actually don't know ahead of time. There may be several solutions. Even there are cases where there are infinitely many solutions. Right? The idea is we're just not guaranteed anything. We don't know which until we actually start to solve the problem. Right? So that's what not having this theorem backing you just means that you're working in the dark. You really don't know. You're taking shots in the dark. You don't know if a solution is out there, what it would look like, how many of them there are. You don't know anything. Right? So we now do not have the luxury of just guessing what a solution is. And then if I find one random one, I can know, oh, that's every possible solution that could ever exist. Anyone who doesn't agree with me is wrong. Like you no longer have that power, right? So that's what is going on here. And in fact, we can actually solve this ODE. How would we go about solving that ODE? So for this particular function, the existence and uniqueness theorem does not apply, which means we're not guaranteed to find a unique solution. That does not mean a unique solution doesn't exist. However, it doesn't mean a unique solution exists either. It's possible that this thing has no solution. It's possible that it has a unique solution, possible that it has several solutions, 5, 17, 12. It's also possible that there is an infinite number of functions that will solve this. We just don't know. And yeah, separation of variables would be the way that we go about solving this. So this one is, so to solve, this one is possible. We would just separate the variables. dy, just move the y minus 3 to the 1/3 under, and here we'll have xtx just by separating the variables. Y minus 3. Okay. Then we can integrate both sides. So I would add 1 to the power, divide by the new power. So then I would have, I can multiply both sides by 2. Then divide by 3, so I have y minus 3 to the 2/3 equals x squared over 3 plus a constant. And so I can get my y is equal to, well, it's going to be plus or minus a square root. So we already don't have a unique solution. That's going to be 2 solutions that way. And then I add 3. So we already have 2 solutions here. Initial conditions, y of 3 equals 3. This means, just by, let me plug into this here. Y of 3 equals 3.
Yeah.
Hold on. Okay. I just muted. All right, so y of, okay, so y of 3 equals 3 means that on this side I have 0. And so I would get on this side, if I plug in 3 for x, I would get 9 over 3, so 3 plus c, which means that my c is going to be minus 3. And so I can get that my y is equal to 3 plus or minus the square root. By the way, this should actually be cubed. So I take the square root and then I would cube it and then I would add 3, which means c is still going to be minus 3. So this would become x squared over 3 minus 3 squared cubed. Okay, so that is actually the solution. Now what I want you to recognize here is that there are 2 solutions to this first order. Then what can you also and exclamating here, y equals the constant function 3 is also a solution. And this is something that you always check, especially when you don't know a unique solution exists. Always check if constant solutions will work if you don't have a guaranteed existence. So how do you know to even look for that guy? Well, it's just something that we know that we have to look for. So if we look up at the top, we have y of 3 equals 3. It turns out that if y is a constant function 3, then y of x is going to be 3 for all possible x values. And so a constant function will automatically satisfy this initial condition. And so now you'd realize that if I plug in y equals 3, this right side gives me 0. And if my y is 3, then dy dx will also be 0. So the constant function 3 also solves this ODE. Other than that, here are 2 solutions. So this ODE has 3 solutions. And by the way, we weren't guaranteed any of them, right? So yeah, there's an example, right? Once either the function or the partial derivative with respect to y doesn't work out, then you're not really guaranteed anything. You don't know if there's a solution, if it's unique, if there's more than one, if there's infinitely many, if it's constant, if it's not constant, you don't know anything. So you just kind of go by whatever technique you think you can find. Hopefully you find a solution that will satisfy your needs. Hopefully you can find all solutions, but none of that is guaranteed. Right? And all because we are at a location where our function and the derivative partial with respect to y don't work. They're not continuous. And when that happens, things like this will happen. You can have a first order ODE with 3 solutions or something random like that. Now, notice what will happen if I look at this case. So this is going to be actually the same guy. Right? So here's the same guy. Now, notice that f equals x times the cube root of y minus 3 is continuous. Around 3, 3. Also, if I were to take the partial with respect to y, that would be a third x y minus 3 to the minus 2/3. And this is also continuous. Around 3, 3. because when I plug in 3 here, it's not 3 comma 3, sorry, it's 3 comma 30. 3 comma 3 would be bad. 3 comma 30. Because now if I plug in 30 for y, I'm not dividing by 0. This guy is actually going to make sense. It's going to be continuous. Same thing if I plug in 3 for x, no problems there. So you know what this means? This means we're guaranteed to find a unique solution. Which means as we're going through the process, you're going to realize that certain things are going to happen, that it's going to get rid of any extra solutions that we're going to have. Everything will collapse into one solution. It's guaranteed. And you might think, well, we just actually saw this, and I see a plus or a minus here and all kinds of stuff going on. How can we possibly get only one solution just by shifting where we're starting? Well, let's see. We'll start out very similarly by separating the variables. That should be 1/3. Then we can integrate both sides. So this is y minus 3 to the 2/3 times 3/2. This side is going to be your x squared over 2 plus a constant. Here, let's actually plug in the initial condition. I can multiply both sides by 2. And if I plug in the initial conditions, y of 3 equals 30. This means on this side, I can plug in 30. And on that side, I can plug in 3. And I can actually solve for c from that. And in fact, let me just also. Right. So my c would be 3 times 27 to the 2/3. Let me move this guy over to make it look a little nicer. I just want it to look a little nicer, over 3. So this here is going to be, well, 3, looks like, and plus c. And so now my c is this constant, 27 to the 2/3 minus 3. And I can go back and solve. So, right, so now I have y minus 3 to the 2/3 equals x squared over 3 plus 27 to the 2/3 minus 3. And boom, I would get y equals, it's going to be 3 plus or minus the square root of x squared over 3 plus 27 to the 2/3 minus 3 cubed. But here's the thing, you're going to notice that this negative sign must be rejected. Since, and you can check this, y of 3 equal 30 would be violated if I keep it. Right? Because if I plug in 3 for x inside here, I would actually get this whole square root would actually simplify to 27. And if I take 3 minus 27, I would not get 30. However, if I take 3 plus 27, I would get 30. So that gives us the actual solution. So that's the solution. Also, you can check y equals 3 is no longer a solution. Because again, that would violate the initial condition. Right? If it's a constant function where the output is always 3, how am I going to get it how am I going to get it to output a value of 30 when I plug in 3 for the input? You can't. It's impossible. This leads to the fact that y equals 3 plus the square root of x squared over 3 plus 27 to the 2/3 minus 3 cubed is the unique solution. So that's just to show you, like, it's almost magical. The universe is going to like literally conspire to get you to the one solution that you are meant for, right? So as long as we have these conditions fulfilled, you're guaranteed to have a unique solution. If these conditions are not fulfilled, then you don't know. The thing you're looking for might have no solution. It might have a unique solution. It's possible. You're not guaranteed. You might have several solutions. You might have infinitely many solutions. You just don't know ahead of time. And I think these two examples illustrate that nicely, because it starts out, we're thinking that we're going to get in trouble because we got in trouble the last time. But it just so happens that because the change in our initial conditions changes where our functions are continuous, it changes the region that we are on so we can get our functions to be continuous, it turns out that things work out in the end. Now let's look at some other things. Now this is something that I see asked from time to time in finals, so I want to make sure that you know how to do it. But that pretty much ends our discussion on the first order nonlinear homogeneous solution business, and just illustrate how reading the theorems carefully can get you in trouble or can help you, depending, especially in a multiple choice. The thing with multiple choice problems is they tend to not be as difficult to actually work through the math. However, if you are not if you don't pay attention to details and you don't pay attention to every little part of this random theorem that's given, it's easy to get you mixed up and you're going to choose the wrong answer choice. So you have to be very careful. It's not just saying everything that looks like this has a unique solution. That's not what the theorem says. It says if we have the continuity requirements over here, that the function over here is continuous and the partial with respect to y is continuous, then we can say this will have a unique solution. In other cases, we cannot say, right? So I can easily ask a multiple choice. Given this first order linear ODE, are we guaranteed to find a unique solution? And if I were a betting man, I would wager that I would catch at least a few students saying yes to that question. Whereas the actual answer is no. You need extra conditions to ensure that you can have a unique solution. You need this in the nth order linear case, you need all the coefficients to be continuous on the interval. In the first order nonlinear case, you need the original function and its partial derivative with respect to y to be continuous on the region that contains the point. Sure, the theorem here says some rectangle, but it can work for general regions. Essentially, you can fit a rectangle into any connected region. So simply connected region anyway. But instead of saying simply connected region, I think they're just like, let's just say rectangles. Everyone's gonna understand that. The people who took 392 should understand what a simply connected region is. Or if you took any vector calculus class, because a lot of the theorems in vector calculus also require simply connected regions. Okay, Now let's look at some other things. And this is not directly related to first order nonlinear or anything like that. This is just in general ODE questions, right? So this is something that comes up from time to time, determining the interval on which you can find a solution, or the region on which you can find a solution, okay? So for the most part, there's nothing else for me to teach you about these. So we're just going to jump in and do some examples and see if you can kind of follow. It shouldn't be too hard to follow. And so here's the second set of examples I want us to go through. Determine the longest interval in which the initial value problem of the nth order ODE will have a unique solution that is n times differentiable. Do not attempt to find the solution. So I don't want you to find the solution. I just want you to tell me, where would that solution live? Tell me the largest possible interval where such a solution would be found. Where should I be looking for a solution to this initial value problem? That is the question. Okay, all right. I think I will turn it over to you guys. Maybe someone can tell me. Give you guys a minute. Tell me the largest possible interval on the real line where I can find an answer to this initial value problem, which happens to be a second order, which means we are looking for a twice differentiable unique solution. Where is that guy going to live? Any guesses? Any suggestions? Or what are you guys thinking? Okay, maybe we can do this. Just tell me, based on what we've been covering over the past couple of days, the existence and uniqueness theorems. Just tell me in a sentence or a phrase where you would expect to be able to find a unique solution. If you were to describe in a sentence where someone would find a unique solution, what would you say? We have a second order linear ODE here. Where would you say we can find a unique solution? Any guesses? Maybe someone should tell me what they're thinking, because I don't know if you're thinking too complicated or you're thinking too simple, or where you guys are actually, where your minds are at. I don't know. Like, we're not in person where I can like watch people's facial expression to see if they're coming up with an answer or they're like totally confused and there's a blank look on your face. I can't tell. So someone should maybe tell me like whatever you're thinking right now. Or just tell me like, I'm totally blank. Just take a survey of all the blank people in the room. Okay, okay. You're confused, no idea. All right, I hear you. Totally confused, blank look. All right, okay. All right, so let me go through this. At least a few people are confused. Some are so confused they can't even remember how to type. I'm confused. All right, so let me go through and tell you. Referring to C when talking about the interval? I don't know what you mean by C. Are we referring to C? What's C? No, you won't need to care, because like you're not even going to know what the C's are unless you actually solve the problem, which you don't need to know. Okay, so the existence and uniqueness theorem for nth order linear ODEs tells us that given an nth order linear ODE and any random set of initial conditions, you are guaranteed to be able to find a unique solution on any interval where blank happens. I could put this as a multiple choice problem and give you a bunch of options. And the option may or may not be there. And you can say none of the above, or you can pick the actual option. But the completion of that statement is where all the coefficients are continuous functions. So that's the thing. You are going to focus on the coefficients. Need coefficients to be continuous. So when someone asks a question like that, you immediately focus on the coefficients. The coefficient here is 1. The coefficient here is the cosine. The coefficient here is ln. Now, in theory, you all know how to recognize whether something is continuous or not almost at a glance by this point, because you've been doing a lot of that in Calc 1, Calc 2, Calc 3. Just, is this continuous, that continuous, that continuous? You should be able to recognize it. The only one here that has a problem is the ln. There's a potential problem here. So at this point, you'd realize that the ln of absolute value of t is not continuous at t equals 0. And the existence and uniqueness theorem tells us that we're guaranteed to find a unique solution on any open interval that contains the input of the initial conditions, as long as all your coefficients are continuous on that interval. So now that we know that 0 is a problem, so here I'm looking at the real line, and you know what? 0 is a problem. So now it means that you have two possibilities for where the solution can live. So this would mean solution is either here, which is the open interval from 0 to infinity, or here on the open interval from minus infinity to 0. It cannot be on any interval that includes 0. Because at 0, I have a discontinuous coefficient. How do I know which one to pick? Well, my initial condition, but the initial condition occurs at y of 2 and y prime of 2, which means I need to choose an interval where 2 actually fits. So if I look at where 2 would actually fit, here's the 2, and I go up and I look, which one of these intervals would include 2? Well, there would be a 2 somewhere over here, which tells you this is the interval we want. And so that ends up being the answer. That is an open interval where, for this ODE, we are guaranteed to find a unique solution to this initial value problem. Okay. Hopefully that kind of cleared up the confusion. To make sure the confusion is cleared up, how about you guys bite on these examples right here? Undo. Didn't move them. Boom. Boom. The n times differentiable part is not irrelevant, but it's given for free because of the existence and uniqueness theorem. The existence and uniqueness theorem automatically gives you the fact that the solution would have n linearly independent components. It automatically gives you the fact that the solution will be n times differentiable. It tells you a lot about the nature of the solution as well. So not only does it tell you a solution exists and that it's unique, but it also tells you, the existence and uniqueness theorems also tell you about the nature of that solution. Being n times differentiable for an nth order linear is one of the things that we get for free. So it's not that it's irrelevant, it's just that it's not something we need to consider. Once we find an interval where the coefficients are continuous, we automatically have the fact that the solution is going to be unique there, that the solution will exist there, that will be n times differentiable there, that the homogeneous version of the solution will have n linearly independent solutions there, that the general solution would look like C1y1 plus C2y2 plus dot 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 Cn there, that if there is a non-homogeneous case, the solution is going to look like C1y1 plus C2y2 dot 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 plus Cnyn plus yp there, right? All of these things we actually get for free just by identifying an interval where the coefficients are continuous. So it's not strictly speaking irrelevant, but it's not a factor in actually answering this problem. Okay, all right, so I'll give you guys like 3 minutes. Solve these ones that I have here, and then we'll move on. Okay, hopefully you guys are getting close to the end, less than 30 seconds. All right, give me some answers, guys. B. What did you get? Now, B has an additional trick into it. I don't know if you guys would see it. Maybe I should have reminded you of the... Okay, so hold on. Hold on. There might be some tweaking necessary. Here is the existence and uniqueness theorem for nth order linear. Okay, now look at that very closely. Take a picture. I'll give you 5 seconds. 5, 4, 3, 2, 1. Now, based on that, would you modify your answer any? There should be a P0 here. I don't know if someone changed their answer, but this probably had something to do with it. So based on what I just showed you guys, would anyone have changed their answer? I'm just fixing a typo here, so you can ignore me. I'll give you guys a few more seconds if you want to. Is that your final answer? Doo, doo, doo. Okay, let's actually see. So if you read the theorem very carefully, you would realize that, and again, I know it's going to seem like I'm trying to catch you, but I want you to be aware of all these traps that can show up very easily on a multiple choice test. And you won't even realize that you're getting something wrong. You will feel confident, like, yeah, I definitely got the answer, but right. Because that's how a multiple choice test can actually get to you. So what you will notice in the existence and uniqueness theorem, as stated, is that it is written in standard form, which means before you even start the problem, you actually need to rewrite this in standard form. You'd have to divide by the x minus 2 first. Then you realize that we have discontinuities at x equals 2, in addition to all the ones you guys would have found for the tangent, which I know you guys are seeing some of the tangent ones because of it's undefined at odd multiples of pi over 2. So we have problems at x equals 2 and x equals n pi over 2, where n is odd, right? So now, when you look at all the intervals, so here's the real line. 2 is first of all, let's put in all the odd multiples of pi over 2. So here is just our 0 for reference. So there's going to be a pi over 2 there's going to be a 3 pi over 2, there's going to be a 5 pi over 2, etc. There's going to be a minus pi over 2, there's going to be a minus 3 pi over 2, there's going to be a minus 5 pi over 2, etc. And then there's going to be an issue that occurs at 2. Now, where does 2 actually show up? On which of these intervals would 2 be? Well, your 2 would end up between these guys. I think it will be closer to the pi over 2 version, but it's going to be like here. So all of these guys here are the bad points. Like, we cannot touch these guys. And now I realize that there's a typo in the question, actually. Because I wouldn't be able to find any solution to 2. I just had 2 in my head. And that's 3. Let's just change that to 3. The 3 would actually be in there. So let's say the 3 is in here, which I care about. Because 3 pi over 2 is 4 point something. It's bigger, right? So it means that this is the interval that can get me what I want, the open interval. So you find all the problem spots. You find the largest interval that has your initial condition, the input part of your initial condition in it. And at the same time, it doesn't go over any of the problem points. So here, the required interval is 2 to 3 pi over 2. Are you guys seeing it now? Are you also seeing the fact that you really have to have attention to detail, that you really have to be careful how you're reading these theorems? Because especially on a multiple choice. Especially on a multiple choice. It's going to be a problem like this. While strictly speaking, I mean, look at the calculations that we do. It wasn't that hard, right? You wrote it in standard form, figure out where these guys are undefined, you plot these on a number line and pick the spot that fits your initial condition, right? Most of these skills come from Calc 1, Calc 2. You can recognize that this guy's discontinuous at x equals 2. You can recognize that this guy's discontinuous at odd multiples of pi over 2. These are things that you would, in theory, be able to recognize very readily. And then you just pick the region that fits your initial conditions. I'm not sure what you mean. What do you do with the y prime? Which y prime are you referring to? This y prime? You don't do anything. The important part of the initial condition is the input. Remember, the theorem says, again, to read into it more carefully, it says you can find a solution to fit any random set of initial conditions given. Meaning, even if I had put, instead of a 3, I had put 27, and instead of this, I had put pi over 6, nothing in my answer would change. Nothing at all. Because you are guaranteed a unique n times differentiable, n component-wise linearly independent solution that will fit any arbitrary set of initial conditions given. So the value of the initial conditions, it's important when you want to actually find a specific solution, But in terms of where that solution is live, where it exists, if it exists, the values of the initial conditions are irrelevant. So when you're looking at the initial conditions, it's the inputs that's important, the half. You need to make sure it works where t is a half, for example. And in this scenario, again, we'll do that thing where we first write it in standard form. That will mean it looks like this. Right? And I mean, even and this guy, you can even think of that as simplifying. It's not going to even matter. And so now we already have a guess by Eugene. So now you'd realize problem areas. T equals 0 and t equals 1. And so now you would say, okay, do on my number line, I have to avoid 0 and I have to avoid 1. And then I realize, oh, my initial condition fits in here at a half, which means this is going to be the interval that I want here. So sometimes you'll realize, why is this important? There are sometimes when you're faced with a differential equation that's very important for you to solve, but you don't really have a nice technique to get to the solution. But it's very important that you have the solution. So maybe what you can do is use a computer to help you find the solution or whatever, but then you have to tell the computer where to look. Because you see, if you don't understand the statement of your problem, you can set a supercomputer to look for a solution over here, and the computer will literally take forever and not find any solutions because there probably are none that would fit the situation you want to solve. You need to know where should you even be looking, right? And that is important. And the existence and uniqueness theorem will help us to determine that. Where should we even be looking for a solution? Where is one even going to exist, right? Now, your machinery, all this technology and machinery that you would have to figure out these things, they're going to be useless unless you know where to direct them. This one is a little bit more general. Determine the intervals, plural, in which a solution is sure to exist. So here I didn't give you an initial condition. You only had to find like all the intervals. And here, again, you do the same thing. You'd rewrite in standard form. Then you'd realize the problem points are right. X equals plus or minus 2. Then you'd realize, okay, so I have to avoid those guys. So I have to avoid minus 2. I have to avoid positive 2. Well, that gives me 3 intervals. So I have the interval from minus infinity up to minus 2. I have the interval from 2 to 2, minus 2 to 2, and I have the interval from 2 to infinity. And these are all the potential intervals where a solution is sure to exist, unique solution guaranteed. So the required intervals are. And now once someone gives you an initial condition, you can now cut down and identify specifically which one of these intervals you want to look at. So there are 3 possible areas that you can actually find for the solution here. right? What else do we want to know? This is the last one. Okay, suppose you have a function, y equals sine of t squared. Can that be a solution to a second order linear ODE on an interval containing 0? So someone has a second order linear ODE. They have an initial condition given when t equals 0. Now someone can try to guess what a solution is, and there's nothing wrong with that. We do that all the time. So someone guesses, maybe y equals sine t squared is a solution to this thing. Maybe we can build off that. Is that guess even possible, is what this question is asking. Could sine of t squared be a solution? Why or why not? And let's pretend that the p and the q are continuous functions. Why could it not be? I'm not sure what you mean by the root is imaginary. So here's how you would think about it. Try to find the derivatives and plug in. So the derivative of this would be 2t cosine t squared. The derivative of that would be 2 cosine t squared minus 4t. And so essentially what you would be able to say is that, now sometimes you can get to a point here where you realize, you know what, after I plug this guy in, it's going to, and I try to put things in standard form, it's going to be a problem. But for this one, there's no obvious problem just yet. However, if you write these guys up, this is a function. Now I can group like the cosines. So I would have cosine t squared times 2 plus 2p. Kind of running over the time I wanted to spend on this section. Let's actually hurry this up. 2pt plus q minus 4t squared. And here, since right, we'd plug in t equals 0. I was going to say something first, but maybe I should plug that in first. So now at t equals 0, this means I would have this here would look like 2. And I'm leaving not plugging in t equals 0 here for a very specific reason. Plus, so that what I was going to say before would have made even more sense. Although you can do it. I mean, I wanted a more sophisticated answer using the Wronskian, but I guess you can actually just you here get 2 equals 0, which is of course crazy. But there's another situation where it might not work out as nicely, and what you can use is the fact that these two guys here are supposed to be linearly independent, and so right, we know that the cosine and the sine function are linearly independent, and so you can actually get a contradiction in the coefficients. So the answer is no. Y equals sine of t squared cannot be a solution. I was hoping this one would be a little bit more sophisticated, but whatever, not complaining. I wanted to rush anyway. All right, so that's that. So first order nonlinear equations. Provided the function and its partial with respect to y are continuous on some region containing the initial condition point, then we are guaranteed to be able to find a unique solution where f is just the right side. You solve for the y prime, everything on the right side is your f. We did some examples where we show how this can break and how it can be fixed simply by looking at a different point. And then we looked at where solutions can exist. This comes down to finding when we put an ODE in standard form, where would all the coefficients be continuous? Choose the interval for which the coefficients are continuous, and at the same time, the inputs for the initial conditions live in those intervals. Also, you should be able to know when a guess is good or not based on how the Wronskian would behave, based on how the function is going to behave when you plug it into the interval, based on how you know a second solution would have to behave based on how a first solution looks like. These were all things that were on the test, by the way. I asked questions like, if we know this is a solution, how many other solutions are there, and things of that sort. So all those little concepts can come together to form something. Now, let's talk about series. Now, at this point, I don't think I'll get through an example of actually doing one of these guys. An example of actually solving an ODE using series. But for the remaining time, I can at least give you guys a crash review of series so that when I do jump into solving ODEs with series, which, oh man, that's gonna be till next week now, today, Thursday. I want to actually start that here today. But after going through this crash course, and again, this review, you don't have to take notes or anything, just kind of listen. And because most of these you should actually already know, I'm just reminding you of some things that you may have forgotten about series that will be important. So let's jump into it. So first of all, you need to know a sequence, right? A sequence is just a list in a definite order, a list of numbers in a definite order. You can think of it as a function where the inputs are 0, 1, 2, 3, etc. And the outputs are A0, A1, A2, A3. You can have an infinite list, which goes on forever. You can also have a finite list or a finite sequence, which ends at some point. We say an infinite sequence converges if you can find the limit and gives you some real number L. If L does not exist or it's plus or minus infinity, then we say the sequence diverges. Make a note of that typo. If a sequence converges, we can write AN approaches L, and that would be shorthand for the limit of AN is L. You always take the limit as n approaches infinity. A series is just the sum of the terms of a sequence. So this is the notation here. A sub n You put this sigma notation, it's called, and that just means you're literally adding all these guys up. You get what's called an infinite series. Or you can have a finite series. It terminates at some point. Either way, we are mostly going to be concerned with infinite series. The finite series are too easy. We'll leave that to the first graders. So here, sometimes it turns out an infinite sum actually adds up to something and makes sense. When that happens, we say the series converges. And we say it converges to a real number S if the sum is a finite number S and it diverges otherwise. When it converges, we can write the series equals that number, right? So kind of like how we can say, like the series n goes from 1 to infinity of minus 1 to the n over n is actually minus ln2. Or we can talk about the series n goes from 1 to infinity of 1 over n squared is equal to pi squared over 6, etc. Right? These guys actually add up to an infinite, to a finite value, believe it or not. Okay, but these are the things you would have seen already. Right, so the number is the limit of a sequence of partial sums. A partial sum just means you're adding up the first n terms of the series. From this, you can create a sequence. The sum of the first term of the series, then the sum of the first 2 terms of the series, then the sum of the first 3 terms of the series. You can create a list, and if that converges to a number, then the series will converge to that number. In fact, I'm teaching Calc 2 this semester where I went over series with them and I expanded on a lot of all of this, but for the most part, you should know all this already, so it's not a big deal. A power series is a very important kind of series, and it's just a series that has this form. Here is an example of a power series, and by just writing out the first few terms, you can start to realize why something like this might be useful. So notice that if I start to write out some terms of this series, I get something very useful, very familiar, very convenient. It's easier to see if I just let x naught be 0. X naught is the point in which the series is quote unquote centered about. If I write that out here, you'll start to see that this series looks like a very familiar object. And that's right, it looks like a polynomial, an infinite polynomial, a polynomial of infinite degree. So you can think of a power series as just an infinite degree polynomial. Now, the nice thing about polynomials is we can do a lot of nice computations with them very easily, including calculus. We can integrate them, we can differentiate them. Polynomials are very nice, they're continuous everywhere, and all that good stuff, right? So polynomials are a very nice function. By the way, where did the term power series come from? It's because the function of a form x to the n is called a power function, and we have a series of such functions, so it's called a power series. Turns out that power series always converge. It's just a matter of where. Either they will converge only for x equals x naught, the center point, when I plug in x equals x naught here, or they will converge for all possible values of x. They converge on the entire real line, as we say, or they converge on an interval of finite length called the radius of convergence. We can call all of these radius of convergence. Radius of convergence is 0 in this case, it's infinity in this case, and it's a finite number in this case. The interval of convergence can come in several different flavors, whether or not the endpoint should be included or not. But that's essentially what an interval of convergence is. And we make the convention r equals 0 if there is no such interval, r equals infinity if it converges on the entire real line, and r is just some positive real number if it converges for some interval of finite length. Figuring out where a series converges or if it converges, you have to do series tests for that, which you covered in Calc 2, which we don't really need to know how to do here, so I'm not going to talk about that. What we do need to know about is what it means for a series to converge absolutely. This was in fact mentioned up here. Power series, when they converge, they would converge absolutely unless they converge at one point. And converge absolutely just means if I put absolute values around each of the terms and add them up together, then that series will still converge. If it doesn't converge when I put absolute values around it, but it converges without the absolute values, we say the series converges conditionally. So there are 2 ways in which a series can converge, absolutely and conditionally. Absolutely means it converges with absolute values. Conditionally means it converges only without absolute values. If a series does not converge in either one of these 2 ways, of course, it diverges. Now, why is knowing about these 2 types of convergences important? Well, as we learned in Calc 2, there's something called the Rearrangement Theorem, which basically says commutativity of addition only works for absolutely convergent infinite series. Meaning, if you have a conditionally convergent series, then you can actually get a different answer by rearranging the terms. So the order in which you add things will actually matter when it comes to an infinite series for if it's conditionally convergent. This is a problem. However, absolutely convergent series do not suffer from this problem. An absolutely convergent series will add up to the same thing regardless of how you arrange the terms. However, this is a problem for a conditionally convergent series because we're going to be doing things like wanting to differentiate a series. So if I know that this guy here, maybe I should put that in red because this is a problem. Let's say this guy here, an x to the n equals a0 x0 plus a1x plus a2x squared plus da 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 is conditionally convergent. Then, well, it's actually impossible for a power series, but whatever. Then, if I were to do something like to differentiate each term, you know, a plus a1x plus da da da, then this would be, looks like I differentiate the first term plus differentiate the second term plus dot dot dot. Now it turns out if this guy can be arranged, if we can rearrange this, and change the answer, then it means that over here is meaningless. Because if I can change the answer by rearranging the terms, then my derivative now becomes undefined because the derivative won't be able to distribute across the sum. So knowing that a series is absolutely convergent is absolutely important. It's absolutely necessary. Otherwise, our calculus won't work, and a lot of other mathematical manipulations won't work. It also won't work with integration or any of that stuff. However, when a power series does converge absolutely, it allows us to perform term-by-term differentiation. Basically what this means is that I can differentiate a series by differentiating the terms of the series and adding them together. This gives us the power to switch the derivative sign in the series sign. This is not true in the conditional convergence case. Does not hold for conditionally convergent series. So that's going to be important. We are going to want to know how to differentiate series in the future. Right? Because essentially we're going to solve ODEs by pretending there's a power series solution. And in order to be able to plug into our ODE, we're going to need to be able to take derivatives to plug into the ODE. So if we can't differentiate the series, that is a problem. And we cannot differentiate a conditionally convergent series. So luckily for us, power series are always absolutely convergent on their radius of convergence. So we are okay there. Now, sometimes you want to find a power series that represents a function. So I have a function, but I instead want to replace it with a series. In the event that the function is infinitely differentiable and the derivatives don't get too big, go back to Calc 2 to find out what that means. You can find a power series using a Taylor series method. And basically, that looks like this. The coefficient can be determined by f to the nth derivative evaluated at the centered point divided by n factorial. Writing out a list like that will create a power series that if it converges to the function, it can actually be used to represent the function, meaning you can interchange them. The power series and the function are one and the same. You can use these formulas to derive these guys. So there are some power series that you are expected to have memorized since Calc 2. These are them. The function 1 over 1 minus x is the series from 0 to infinity of x to the n. This works for a radius of convergence of 1 because it works specifically on this interval. e to the x can be thought of as this series. Cosine of x can be thought of as this series. Sine of x can be thought of as this series. These series here for these three work on the entire real line. So at any point, you could go back through all your notes and everything. Every time you see one of these functions, you can replace it with one of these series, and it would make no difference in anything you've ever written down your entire life. One can be switched with the other, and no one is going to know the difference. It's that powerful. And of course, this side looks like a polynomial, which is nicer to deal with than this guy in many cases. So using these series, we can derive a lot of things that we already know about our functions. So for example, just to show you, well, this one is just going to be straightforward. Here, I can just plug into the series. Instead of x to the n over n factorial, which I know is what e to the x is, I can plug in the minus x squared. And so a power series that represents the function e to the minus x squared would be this series right here. Now that series is useful because this particular function here, e to the minus x squared, super useful in probability and statistics, and we want to integrate it all the time. However, you might have recalled from Calc 1, that guy does not have an antiderivative. So if you try to integrate it using the fundamental theorem of calculus, you are going to be in trouble, can't work. However, you can integrate this guy over here. You can integrate this series because it's just integrating a polynomial, an infinite polynomial. And what you can do is you can integrate each term of this guy, plug in the endpoints, and apply the fundamental theorem of calculus to the right side. You'll have an answer with an infinite number of terms that won't converge to any function that is meaningful in your calculus vocabulary. However, you can approximate that within any desired accuracy you want. To convince you that we can actually do things like find derivatives of series, here are some examples to convince you of that. So that when I start differentiating series later on, you'll know that, yeah, I'm kind of convinced that that's actually a valid thing to do. So for example, knowing that e to the x is the series x to the n over n factorial, and knowing that this is absolutely convergent for all real x, I can now switch these guys. This can be switched because of absolute convergence. We couldn't switch it otherwise. And now you can just differentiate that by bringing one down and subtracting one from the power. Of course, you guys remember about factorials. This is just a series. N goes from 0 to infinity of x to the n minus 1 over n minus 1 factorial. And here you'll realize that that is equivalent to, because you can't have like a negative factorial, at least not in the real version. So you'd actually skip this first thing. It's actually equivalent to that. We can do the same thing. So you get e to the x, the derivative of e to the x is e to the x. Right? So if that didn't convince you, I don't know. Maybe this will convince you. You can look at the power series for sine of x. And again, this was all done in Calc 2, so that's why I can rush here. I can realize that this is differentiating the series minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. I can switch this because of absolute convergence. And now I'm just differentiating what's called term by term differentiation. So bring the power down, 2n plus 1, x to the 2n, subtract 1 from the power, over 2n plus 1 factorial. You'd realize that the 2n plus 1 cancels this 2n plus 1 out of the factorial. And you'd realize that that would give you the series n goes from 0 to infinity of minus 1 to the n x to the 2n over 2n factorial. And you should recognize that as the cosine function. So here we just derive the fact that the derivative of sine is cosine. And we did it using series. Just to kind of convince you that the series and the function are interchangeable. Everything you could have done with a series, you can do with a function. And I just decided to show you those. These guys also show up every now and then, the hyperbolic cosine and sine. Notice that they look like cosine and sine respectively, except they're not alternating, which makes you think mathematicians knew what they were doing when they named these guys the hyperbolic cosine and the hyperbolic sine. These will be some useful properties of series. You can factor constants out, so you can move a constant in and out of a series, a constant factor. I can also combine or expand series of this form. Usually we're going to want to do the combination. You should know that series do not distribute across products, so don't do that. Although in practice, we're never really going to see a situation where we have to do that because we're only going to solve nonlinear ODEs with series. Another thing you should know is that you can start a series at a different point by evaluating a few terms. So if I have a series starting at 0, but I don't want it to start at 0, and we'll see situations in which why we don't want to start at 0, what I can do is just evaluate the 0 term and start it at 1. Or I can evaluate the 0th and the first term and then start it at 2. Or I can evaluate the 0 and the first and the second and start it at 3, and so on. Whatever is convenient, we can start it off at a different point by just evaluating the first few terms and then starting the series from the next term onwards. That's going to be important later on. Because we can only combine series when they start at the same point. So to get the series to start at the same point, I might have to do something like this, after which I can combine them into one big series. That's going to be very important. Another useful manipulation is shifting the series. For example, given any series, I can make a shift at will by adding or subtracting something to the variable. So if I see something like this, and I see an n minus 3 in the power here, and suppose I want an n in the power, I can shift all n's to n plus 3's. This includes the n that's on the base of the series here. If I go to this series and change all n's to n plus 3's, rewrite it, I would be able to write this series as that series. And this guy and that guy are saying exactly the same thing. They will both add up starting from a4 x to the 1 power, then a5 x to the 5th power, etc. They are both going to say out the same thing. So shifting a series, very important. That's something you should remember how you can do. And yeah, knowing all of that, we can finally get to a point where we can actually solve ODEs with series. We're going to look at two varieties of solutions: solutions near ordinary points and solutions near singular points. To understand the singular points, we need to first understand the ordinary points. So that's what we're going to start with. And we're also going to start with soldes, and we're pretty much going to keep in soldes because in principle, if you know how to deal with soldes, you know how to deal with higher orders. An ordinary point is just a point that keeps everyone continuous if you were to put it in standard form. That means the coefficient of the y double prime, any point that keeps it non-zero so that you can divide through by it to put it in standard form, that's called an ordinary point. Any point that makes that 0, that's called a singular point. And those guys you have to deal with very carefully. Ordinary points are a lot nicer though. Basically how we're going to solve an ODE is we're going to assume that the solution can be written as a power series centered at the point that the initial condition is based at. Once you do that, there is a 6-step strategy that you can do to actually solve it. And we're going to do this for these examples next time. You basically assume a solution looks like this. You're going to differentiate and plug into the ODE. You're going to make all the necessary shifts and make all the necessary evaluations. So all the series involved start at the same point. You're going to combine all the series. You're then going to equate the coefficients on both sides to obtain something called a recursive recurrence relation. Using that, you're going to be able to find an equation to find all the ANs. Once you find all the ANs, you just plug it into the series version of your solution, and then you profit. You can say what the answer to that is. Of course, in general, the answer is going to be some series where you don't even know what function it represents, but ever so often, magic happens and we can actually recognize what series, what function is represented by that series, which is why you need to have all these guys I mentioned up here memorized. But once we do that, we can find the series. Now, what you can do is you can copy down these questions here, or just take a picture and try them for tomorrow based on the set of steps that I'm going to give, based on the steps that I gave you. And we're actually going to do all these examples tomorrow. So we're going to stop there. I wanted to do like one example with you, like example A, but the last section took a little bit more time than was necessary, than I was hoping. So for now, just take a picture of those. We'll deal with that. In the PDF, I'll give you the steps. And to actually solve one of these guys using series, I'll put on the bonus problem for your quiz instead of one of the actual problems. Right, it's going to be on the bonus, as I said, because I didn't actually do an example with you. So we do have a quiz next Tuesday. It's on everything right before series, and the bonus will be on series solutions at ordinary points. So you might want to go through and actually try to solve these based on the steps. If you don't get it, not the end of the world. We are going to go through it on Tuesday. And so, yeah, we are going to end right there today. So that's it. Did a lot of rushing there at the end. However, technically it was a review of Calculus 2. So I will let you guys know. The quiz will cover everything we've done since the first test. So everything after the first test. So I guess everything in this past week. And it stops just before series. Yeah, a lot of theory. We're going to get back to the computational stuff like right now. I don't think there's anything major theoretical that's left. Yeah, I think we're done with all the heavy theory. Right? I might mention a few concepts moving forward, but yeah, like nothing is going to be like the last 2 lectures worth of theory. So something to look forward to. It's going to be more computational. The theory is important though, because in a multiple choice exam, they can ask around the theories, ask about the theories. And if you don't really know the theory very well, it's super easy to fool you as to what the correct answer is, or if the correct answer is even present. So I've seen a lot of questions on the final in the spring where it's like, on one hand, it was super easy, but on the other hand, it was only easy if you knew the theorem that the question was asking you about. Then it's like, it's a 2-second problem. But if you don't know, it's so easy to get it wrong. It wasn't funny. And yeah, so I don't want that to happen to you guys. So I'm telling you about the theory. We'll stop there. I will see you guys in the next one. Stay safe, enjoy your weekend, study, and we will start series solutions. Jump into it. It's going to be very computational. I'm not sure if you're going to miss the theory because the computations can get long for these guys, but we will take care of that on Tuesday. And with that, I will say I will see you in the next one. Ciao.